That's the sum of n terms. N. And I think everything else we've already defined. And then down here we have R. And what is R? Ratio. It's the common ratio, and it's the amount you do what? You multiply by. So R is the amount you multiply by in the pattern. Okay. Everybody gets tripped up about the R doesn't equal 1. You can pretty much ignore it, but why can't R equal 1? Look at your fraction.
If it equals 1, it's going to cancel with 1 minus.
Yeah, so that would make your denominator equal what? 0, yes. So R doesn't equal 1 because you can't have a denominator of 0, but you don't have to worry about it. If it confuses you, just get rid of it. You don't worry about it, okay? You know R can't equal 1. So we're going to do some practice problems together. The Osaka Tigers basketball team plays in a multi-level stadium. The most expensive tickets are in the first row. The ticket price in yen for each row forms an arithmetic sequence. Prices for the first 3 rows are shown in the following table. Write down the value of the common difference D. So we're trying to figure out how much are we adding to the prices. Are we adding a positive number or a negative number? Negative, right? Has anybody figured it out yet? Negative what? Negative 250. Can you guys check that? Make sure it makes sense. Are we adding negative 250? All right. Anybody confirm it? Yes? Good. Okay. So D equals negative 250. Calculate the price of a ticket in the 16th row. Now, some of you guys really like to just follow the pattern to the 16th row, and that's okay, but if it asks you the 1000th row, I really don't want you to have to do that. So we're going to use the formula. Which formula are we going to use, arithmetic or geometric? Arithmetic, right? Because it does say it's an arithmetic and it's an adding pattern. And then are we going to use the U formula or the S formula? U, because the S is for a sum and it doesn't ask for a sum. So we're going to do, I'm just going to write the formula to start. U sub n equals U sub 1 plus n minus 1 times D. And then if I want to find the 16th row, I'm finding U sub 16. That just means the 16th term. U sub 16 is the 16th term. And what is U sub 1? That would be the first term. What's the first term? Yeah, 6,800. This is my first term. This is my U sub 1. Okay, since we're finding the 16th term, that is your n. And our D was negative 250. All right, so take a moment to calculate that and then check with your neighbor and see if they calculated it the same. What is it? 3,050? 3,050. Can anybody confirm 3,050? Yeah, thank you. So this one is in yen. I was going to put a dollar sign on it. It looks like the yen symbol is this, which I hadn't seen before. Had anybody seen that before? Yeah. That's, you guys see it a lot more than me. You're very worldly. All right. Why is it? Find the total cost of buying 2 tickets in each of the first 16 rows. I really like how they thought that one through. They thought, you don't want 1 ticket, then you're sitting by yourself, right? So you're going to buy 2 tickets in each of the first 16 rows. Still, it's a little bit off. Like, why? Why would you do the first 16 rows? But anyway, this time we're finding a sum, right? So we're going to find the sum of getting 1 ticket in each row and then just multiply it by 2. Are we doing arithmetic still, or did it become geometric? Yeah, it's still the same situation. It's still arithmetic, okay? So you're going to find an arithmetic sum. Notice that at the top of your paper, you have 2 formulas. So let's think about which formula are we going to use? All right.
That is not a whole formula.
This is a formula, right? And that's a formula. This is my friendly formula. This is the one that Gauss used to add up those 100 numbers from 1 to 100, right? This one is a little bit longer, but why is this one good? Why is that one helpful? So they both have the u sub 1, right? But this one doesn't need what? It doesn't need that u sub n. It doesn't need the last term. So that's the question we have to ask ourselves. Do we know the last term? Oh, we do, right? Because we just figured it out. You guys see that we found the 16th term? So if you want to, you can use the easier formula, but that's up to you. Okay, so take a moment and you can do whichever formula suits your needs, and we should get the same answer. So you're going to find the sum of all of them, and then you have to double that answer since you're going to be finding 2 tickets from each. All right, so my answer key did the problem the other formula, but it said that they got 78,800 for this sum. Did anybody else get that for that sum? You did? Okay. And then we have to multiply that by 2, right? For 2 tickets. And so then they got 157,600 yen.
I'll be typing it back to you.
Ask Kana. It says 2 what? Yeah, so if we were just buying 1 from each row, we would just add them up. But because we're buying 2 tickets from each row, we had to times 2. All right, when you're done, turn the page. Looks like Mia has a very interesting way of cutting her pie. She doesn't cut it fairly, but she does cut it with a pattern. So can't complain about that if you're a mathematician. All right, so Mia baked a very large apple pie that she cuts into slices to share with her friends. The smallest slice is cut first. The volume of each successive slice of pie forms a geometric sequence. That means like the next piece might be twice as big as the first piece, and then the next piece might be twice as big as that. I don't know though, because I don't know what the R is. So maybe it's only like 1.1 times the volume. I don't know. The second smallest slice has a volume of 30 cubic centimeters. And the 5th smallest slice has a volume of 240 cubic centimeters. So let's try to look at those numbers. That's the first, and then the second was 30. Then I've got the 3rd, the 4th, and the 5th, and the 5th was 240. All right, so see if you can use those numbers to find the common ratio. That's the R. That's the number you're multiplying by each time. All right, Sally, what'd you get? Sally says R equals 2. Did anybody else get R equals 2? Owen got that, and Morgan and Steph and Khalil. Anybody else get R equals 2? And Marush got that, and maybe Glory. Okay, yeah, I think that might work. Can anybody raise their hand to share their process for finding R equals 2? Besides like just seeing it, because just seeing it, like that's magic for you, but it doesn't help other people. Anybody, can anybody describe a process that they use? Go ahead, Sally.
I just multiplied 30 by 2, and then 60 by 2, and then 120 by 2.
And
To see if I would get 240.
Okay, so guess and check. Guess and check is a valid process, and it will work if it's an integer because you'll get it eventually. But sometimes it's going to be like 5/4, right? And so I'm wondering what could we do if it's not a nice number like 2? Does anybody have an idea about what we might be able to do? Do you guys remember, like when it was an adding pattern, we just counted up how many times we added? We could do something similar here. We could figure out how many times we're multiplying by, right? How many times did I multiply by between 30 and 240? 3, right? So 30 times R times R times R, so times R to the 3rd, equals 240. So when it's an easy number like 2, I think guess and check is a perfectly good way. But if I'm going to get something like 5/4, I'm probably not going to guess and check that. So it's good to have a way to do it. So if I start with 30 and I multiply by r 3 times, I get 240. If I'm solving this for r, what would be the next step? Divide by 30, good. And I get r cubed equals 8. How do you solve r cubed equals 8? Cube root, yep. So you're going to do a cube root on both sides. Cube root of r cubed, cube root of 8, and I get r equals 2, which is the same thing that you guys kind of figured out on your own, which is super. So that does mean that r is 2, and then the smallest slice, what would be before the 30? 15, right? So you could work backwards. Since it's a multiplying pattern, the inverse is divide, and you could get 15, and that would be cubic centimeters. All right, the apple pie has a volume of 61,425 centimeters. Find the total number of slices she can cut from this pie. So we're talking about the sum here, right? So that's going to be the sum. And we need to find out how many slices n we can get out of that. So let's put that into the sum formula. So from the front, we're doing geometric, right? So my sum formula is u sub 1 times r to the n minus 1. Oh wait, you guys have 1 minus r to the n, right? I'm just going to start over. You have s sub n equals u sub 1 times 1 minus r to the n over 1 minus r. That's the formula we're looking at, right? Because it's geometric. Thank you. Good morning. All right, so we said that the sum is this number, 61425. The first term we just found is 15. 1 minus, we figured out r was 2, but we don't know n. And then 1 minus, oh, not here. Sorry, guys. 1 minus r, which is 2. Okay. So all I did was substitute values into the formula. Does anyone have a question about where I got those numbers from? Okay. So I can simplify my denominator. What's 1 minus 2? Negative 1. And then what is 15 divided by negative 1? Negative 15. So I have 61425 equals negative 15 times 1 minus 2 to the n. What would be my first step in solving for n? What should I do next? Give us a guess. Say it again. Distribute. I might want to distribute in some cases, but in this case, it could be a little bit tricky because of that 2 to the n. You could. I think I'm going to choose to do something different though. Blaine? Say it again. Yeah, so that's what I'm going to do is try to undo this multiplication right here by dividing by negative 15. Sally's idea could work too if you were careful. All right, so let's figure out what that is. Let's divide 61425 divided by negative 15. So I get negative 4095. Negative 4095 equals 1 minus 2 to the n. Now notice that's minus 2 to the n. It's not negative 2 to the n. So order of operations has 2 to the n happening before the minus, just to make that clear. All right, we're going to get rid of the positive 1 by subtracting it. Negative 4096 equals negative 2 to the n. And how can I get rid of the negative? Give me your idea. Add it. So let's see. Add what? Okay, so I could basically just add to each side. I could add this to move it over here and add this to move it over here. You could do that. I'm gonna probably just multiply both sides by negative 1. You could also divide by negative 1 actually, which might be easier to look at, dividing by negative 1. So I get 4096 equals 2 to the n. All right, my exponent is a variable. What kind of equation is that when your exponent is a variable? What's that? What was it? I couldn't hear. A confusing one? Yes, it's a confusing one. But we did study this kind of equation. What kind of equation has an exponent as a variable? So it's it has exponents. Quadratics have exponents, but quadratic is like x to the 2, right? We're doing like 2 to the x. It actually sounds a lot like the word exponent. What kind of equation is it? It's exponential, yes. An exponential equation has a variable in the exponent. What is the inverse of an exponential? Starts with an L. Log. Yep, logarithm. Okay. So you could apply a logarithm to both sides, or more simply, you could rewrite this as a logarithm. And I really want you each to take a try at that. So give it a try. Write down what you think it might look like as a logarithm. And if you didn't remember exactly, that's okay. I just want you to try to get that out of your memory. Log base 2 of 4096 equals n. You don't put the equals n into Desmos, though. So you're going to type log base 2. You can either use the functions, or remember that Sky showed us that if you do the underscore, that also brings you down to base 2. 4096. All right. Ben, how many pieces did you get?
12.
12. That's what I got too. Anybody else get 12? Good. All right, so log base 2, 4096 is 12. So that means that we can get 12 pieces of pi. Of course, the 12th piece is the one I want because that's the super big one. The first piece was the smallest. So n equals 12 pieces. I really like how we just got to review cubic equations with cube roots, and now exponentials being solved with logarithms. This is good prep for a final exam coming up at the end of the month for seniors and June for the rest of us. Okay. Oh, this is like, you know what? Some of these problems are definitely IB problems, because look at this. IB likes to write things in English instead of American. Program, right? Charlie and Daniela each began a fitness program. On day 1, they both ran 500 meters. On each subsequent day, Charlie ran 100 more than the previous day, whereas Daniela increased her distance by 2% of the distance she ran the previous day. Calculate how far Charlie ran on day 20 and how far Daniela ran on day 20. So let's just talk about Charlie and Daniela for a moment. Charlie's pattern, is it arithmetic or geometric? Arithmetic, yep, because it's an adding pattern, okay? So Charlie is arithmetic with a D of how much? How much is he adding each time? 100. All right, how about Daniela, arithmetic or geometric? It is geometric. So she is multiplying her running amount each day, but she's not multiplying by 0.02. That would make it smaller. What is she multiplying by? 121? I think she's 2%.
Oh.
0.2? So multiplying by 0.2 and multiplying by 0.02, those are both going to make it smaller, right? But we know she's getting bigger. So take a moment. 1 point what?
1.2.
You're getting close. 1.02, right. So 2% is 0.02. And then we know she's doing 100% plus 2% more. So she's doing, I'm going to write that down, 100% plus 2% more is 102% each day. So she has an R value of 1.02. All right, so see if you can finish this up. Try to do I, and B. All right, so we're trying to find the 20th term using the arithmetic formula. We got our first term at 500 plus n minus 1, so that's going to be 20 minus 1, that's your n, times d, which is 100. And if you use the formula, you should get 2,400. Anybody get 2,400? Okay. Meters. That's not very far, right? 2,400 meters? No. Okay. Maybe they're sprinters, though. And then it says Daniela ran on day 20. So we have our R value here. We're going to use that formula. So that would be U sub 20 equals A sub 1, 500, times our R value of 1.02 to the n minus 1, so to the 20 minus 1, which is 19. And then for that one, I got 728.4 or 728. Either of those is fine. So it looks like after 20 days, Charlie's still running more. But we know in the long term, an exponential function is going to pass a linear function. One sec. We get these two values, so Daniela's still running less. I made a little chart on the board for you to see like how even though Daniela might be less for a very long time, an exponential curve will eventually pass that linear curve. So that's the question is, when is that going to happen? When is Daniela going to run more than Charlie for the first time? Okay, so we want to know, we can find the point where they're the same, and then it's going to be a decimal. So the day after that will be when Daniela runs more than Charlie for the first time. So we want to know when this one here, when is Charlie the same? When is that going to be the same as this one? So we can graph them in Desmos, but the problem is the graphs are kind of weird. And you don't see much at first. What I did was I graphed them both on their own line. So y equals and y equals. Oh wait, I'm sorry. That should be an n, right? This one should be an, oh shoot guys, that's not at all it. You need to put the first formula in before you put the 20. So it would be 500 plus n minus 1 times 100. Okay? And we want to know when is that going to be the same as 500 times 1.02 to the n minus 1. Okay? And what I'm going to do, and what I want you to do too, is I want you to graph them each on their own line. So I'm going to use y and x. Y equals 500 plus n minus 1 times 100. And 500 times 1.02, and then raised to the n minus 1. Okay, now when you look at your Desmos, it is, oh, I forgot the y equals. It's not going to look like much. Oh, use x. X. Okay, it doesn't look like much. I only see the red one. I don't even see the blue one. You can zoom out a bit. You can like zoom out a lot. Right? But it's still kind of hard to see. Turns out what we're looking for is a point that's way up here. So what we're going to do to see that point is change your graph settings and make your y's go up to 20,000. And your x's don't have to go that big. Your x's can go to 200. Oops, I don't know what I did there. All right, I'm starting to see something that looks normal. So now you see a graph that looks kind of like the one I graphed up there. And we can see that there's this point here where Charlie and Daniela cross. So which of these numbers is going to tell me how many days? Is it the x term or the y term that tells me how many days? Yeah, what does the y tell me? Say it again, Steph. The distance, yeah. So this is the days, this is the distance. They're going to run the same at 184.2, but 184.2 never actually happens. There's day 184, there's day 185. So which day is Daniela going to start running more? It's 185. Yeah, so it's interesting because this would round to 184, right? But she hasn't actually passed him yet at 184. She's still like a little bit below. So it's the next day, 185, when she passes him. Okay? So on my paper, I know you can't see it yet. I'm going to write n equals 184.2. And then I'll say she runs more on day 185. All right. All right, very good.